Hi, this is Kirsten Nicolason, and I'm finishing up part three of the Climate Change 102, What We Can Do. And in this last lecture, part three, I'm going to talk about two types of carbon sequestration that involve regional or potentially national scale technological fixes to climate change. And after that, I'll talk about a variety of personal action items that people can do. Not many of the climate change solutions talks that you hear about are based in geology. And so that's what's different about what I'm presenting today. So technological fix number two is fluid carbon sequestration, where we have carbon dioxide being produced at a power plant. Because coal produces the most carbon dioxide when we burn it, it is also the most efficient type of carbon dioxide source. That is, because it's producing so much CO2, it actually makes it easier to capture that CO2. However, right now, coal prices are not competitive with natural gas. And so coal-fired power plants are not as economical as other kinds of power production. Regardless, we could have CO2 being produced by a cement plant or other types of industry. And the idea would be to capture the carbon dioxide from that power plant and then pump it underground. And that's represented by all of these orange pipes here, where the CO2 is being distributed underground. Now, that could actually uh, serve another purpose, which is if there is oil and gas, a small amount remaining in a depleted oil field, that CO2 can actually act like a dry cleaning fluid and uh, efficiently efficiently remove the oil from adhering to grains in that underground sandstone or underground carbonate formation. And it's a little bit like dry cleaning. It would remove the oil and then allow the oil to be pumped out, like in this blue pipe right here. Here, this might be helping with mining of methane. So these are both falling within the category of enhanced oil recovery. But you can also have a deep aquifer where the water is really quite salty and not at all suitable for any kind of agricultural use or human consumption. And so those deep saline reservoirs actually can absorb some CO2. Now, the CO2 is not really dissolved into the water, it's more like it's existing um, as little bubbles within that saline reservoir, depending on the depth. So, just to summarize, this relies upon separating carbon dioxide in some kind of industrial source, pressurizing the carbon dioxide to act like a fluid so that we can pump it underground. And then in some cases, that would enhance recovery of other hydrocarbons. So, this is a fantastic idea, especially if it's helping recover oil and natural gas. That will help make this an economical uh, way to take care of CO2. And it would remove the CO2 from before it goes into the atmosphere and return it underground where it came from. And it would create long-term storage. In the lower left, what we're looking at is meant to be a cross section of a sandstone, for example, where the pale orange or tan uh, shapes represent grains. Here we would have a grain of quartz. QTZ is representing quartz. We would have another mineral, plagioclase, which is common in arcosic sandstones, and we might have some mica. And here we would have uh, existing between those grains that saline brine that might even have some dissolved calcium within that brine. Well, once we pump our CO2 into that kind of situation, we can have chemical reactions between the carbon dioxide and the brine, and that might lead to a new mineral for that area, a solid calcium carbonate like calcite. So we would actually precipitate or grow a new mineral within this location, and that, of course, is going to be very stable and help with long-term storage. Now, this approach is actually already underway. The Sleipnir oil field offshore of Norway is now injecting carbon dioxide under the North Sea for enhanced oil recovery. Of course, there needed to be new infrastructure built and an incentive to actually make this happen. So Norway imposed a tax on CO2 emissions of $70 per ton of CO2. And this both incentivized the capture of CO2 during oil processing and potentially provided money for grants or loans to build the correct infrastructure. But there are some disadvantages, and that is that it is somewhat difficult and certainly expensive to separate carbon dioxide in these smokestacks. If you have an existing power plant, then you might have to pay for a retrofit, and that could be expensive. You also have to transport the CO2. Now, if your power plant has been built in an area that has the right sequence of sedimentary rock units or even basalt rock units, then you can simply pipe it underground right there. But in some cases, you have a very good target formation, like the Columbia River Basalt Group where I live, but there really aren't very many power plants in the area that produce CO2. We're fortunate to mainly rely on hydropower and some wind power. But there are some other disadvantages or uncertainties. For example, Carey, in his paper in 2013 called The Geochemistry of Wellbore Integrity in CO2 Sequestration, he looked at what kinds of chemical reactions would occur in the pipes themselves, and especially where you put cement, Portland cement, around those well pipes, especially near the surface, because you don't want the CO2 leaking back up. You could have it be injected, but then it could leak back up along the edge of that pipe, and that would not, that would be a big problem. And so right now there's ongoing research that shows that actually you can get new mineralization in the pipe and within the Portland cement that will help seal that pipe from leakage. However, you get that mineralization in part because you have corrosion initially, or the acidity of the CO2 fluid can partly dissolve your pipes. So that's an area of active research. And then, of course, we have a lot of emissions that are not taking place at a single point source. These are emissions from cars and planes. They're diffuse and not easily captured. But right now, I think it's the separation of CO2 that is the step that is somewhat limiting here. Okay, here's another idea, and this is an idea because rock carbonation is happening around us at the surface all the time, every day. This is a natural process. And what we're describing when we talk about rock carbonation is that these are rocks made of silicate minerals, silicon and oxygen bonded to other elements. We also have various lavas, like the Columbia River basalt, where it may have some minerals that grew in the basalt when it was a hot magma, but generally, lavas cool very quickly, meaning that their chemical constituents are in a microcrystalline glass. And that microcrystalline glass actually proves to be an advantage if you're interested in rock carbonation. Excuse me. So this image taken from alongside the highway here in Washington State shows the top of an ancient lava flow. And that lava flow was exposed at the surface for long periods of time. Where this crack is at the top of the pink unit, that was the ground surface. And that ground surface was exposed to rain, runoff, maybe snow, and it would periodically be wet and dry, and that would enhance chemical reactions at that surface. Basically, we would have a chemical reaction, for example, that would take place between the iron in the rock, because there's usually about 12% iron in these kinds of basalts, and it would mix with oxygen from air and water. And in that case, it would form new minerals, one of which might be goethite, which is an iron hydroxide mineral. And this beautiful image on Wikipedia shows the bright orange color of goethite that we might call rust, just casually in conversation. So basically, the top of this rock formation has essentially rusted. What's also important is that there is calcium in this rock, and you can see some little white patches amidst the rusty part of this former lava flow surface. And in that case, we can have calcium in the rock combining with carbon dioxide from the air with rainwater, and that can create new carbonate minerals like calcite, calcium carbonate. So just as a reminder, on the left here, you see a drawing that represents the chemical structure of calcite, where we have, as our main building block, 3 oxygens here surrounding a single carbon atom. And there's another image showing this carbonate group, 3 oxygens, each having a -2 charge, surrounding that smaller carbon cation that has a +4 charge. So the -6 charge of the oxygen and the +4 charge of the carbon are imbalanced. And in order to be stabilized into a mineral structure, they need to find another cation with a +2 uh, uh, charge on it. And it just so happens that calcium can provide that +2 charge, so can magnesium. So this is a natural process between carbon dioxide in the air. It is sped up by the presence of water, and we're leaching calcium and magnesium out of our rocks to create common, natural, and safe minerals. And here are a couple of beautiful examples. The one on the left is under black light to make the calcite glow. All right, um, just as another reminder, magnesium can also help us out with this. So here is a balanced chemical reaction where we're taking moles of magnesium, 10 moles of magnesium from the basalt, liberating it from the basaltic glass. We're combining it with water, CO2, and oxygen, and we're creating a mineral called hydromagnesite. And again, this is a natural process forming a natural mineral that is not toxic. Notice that this carbonate group here is what is going to be removing the carbon dioxide from the air. It's fantastic that this magnesite can accommodate 4 carbonate molecules in its structure. So you might be curious to say, well, this happens naturally, but can we speed this up? Can we make this happen? And in fact, at the nearby Pacific Northwest National Labs, they have been doing research on this for about the last 10 years. They know that there are numerous basalt flows here. They extend nearly 5 kilometers deep in the area of Pasco, Kennewick, and Richland. And so we can drill quite deeply into the Columbia River basalts and then pump in carbon dioxide. Now, this picture at the lower right shows a drill core that's already been taken out of the rock. And you can see that this is not actually from injected CO2, but just from natural water. And we've had an agate form in one of the cavities in the basalt. But these little white patches are where carbonate minerals have naturally grown in the existing holes or vesicles within the basalt. Okay, so this idea of mineral carbonation has been taken up by some industries that are hoping to turn this into building material. So Calera is a company that is wondering, what if it was possible to build with carbon dioxide? And they have created a carbon capture and conversion plant in California. And the idea is that they can take those carbonate minerals and then create panels that can be used for building stones. So the natural carbonation of silicate rocks or carbon sequestration in solid minerals, in the formation of solid minerals, has a lot of advantages. It's mimicking a natural process. It creates minerals that are stable for long periods of time. These minerals could grow underground or possibly under the ocean. And the target rocks that would do this really efficiently exist in the US, India, China, and other countries. And possibly we could create building materials, um, although that is perhaps not yet economically viable. The disadvantages, the natural process is somewhat slow. It's very expensive to separate out the carbon dioxide and pressure it. You need to capture that carbon dioxide near the rock formation where you intend to sequester it. And that is not always a good match. And this rock carbonation is my favorite, and I teach about it in my mineralogy class, but it's not well publicized and it's not yet widely available. So let's talk now about other ways that we as voters and individuals and communities can try to tackle this while we separately work on the technological fixes. So excellent news is that we have done a lot of research into green production of energy. So we can reduce our reliance on coal and natural gas and petroleum, like heating oil, if we're able to produce energy by wind, by tides, and by solar mirrors, constant or mirrors concentrating the sun's energy onto a solar cell. So we've already started those types of projects. However, it's clear that we have so much carbon dioxide in the atmosphere that, and we have not um, reduced our emissions. We continue to produce excess CO2 even now during the pandemic. And so some people have said we really need to look into these negative emissions technologies and reliable sequestration. This is a report from the National Academies of Science, Engineering, and Medicine, meaning that all three of those branches, experts in all three of those branches, have come to consensus that we need to use negative emissions technologies like carbon sequestration and rock carbonation. So because we need to remove excess carbon dioxide from the atmosphere now, you could ask, why is this so hard to do? Well, remember when I talked about those parts per million? If we put 100 tablespoons of sugar into an Olympic-sized swimming pool, that's 2 parts per million. But imagine if you put in 3,000 tablespoons of sugar into your Olympic-sized swimming pool and let them dissolve. You let it dissolve. How do you separate out that sugar again? That's the trick. It's a lot of water to filter, and the particulates have dispersed, making it really difficult to remove. So right now, actually, it's more than 406 parts per million. It's already up to something like 412. But 406 parts per million of CO2 is 20,300 tablespoons of CO2 dissolved into this swimming pool in our analogy. And our goal is that we want to get back to 350 parts per million, which would be about 17,500 tablespoons. So you can see that not only do we want to filter our swimming pool, AKA our atmosphere, but we would need to remove 3,000 tablespoons worth from our swimming pool in this case. We cannot remove all of it. We would overshoot the mark. But removal of excess CO2 is happening now. And this is an image from the spring of 2018, I think, that Switzerland had just deployed these fans. And this is just out in the open, and these fans are pulling the atmosphere through filters, and those filters are trying to sieve out the CO2. This is a neat pilot project, but so far it is not employed at a large scale, and it would be very expensive. So we can then turn to thinking about our personal action options, because trees, plants, and healthy soils are actually always sieving CO2 out of the air. This is a totally natural process that is what the trees use to grow their leaves. Those leaves are little energy factories for helping that tree capture more carbon dioxide from the air and use it to create sugars and starches and cellulose to grow its wood. So what we can do, of course, planting trees is a fantastic option. Composting fruit and vegetable scraps so that they are feeding microorganisms instead of creating methane at landfills. That's a great option. buying forest certified wood so that we don't get clear cutting of tropical rainforests. And then avoiding peanut butter. Most kinds of peanut butter use palm oil to make it that smooth mixture. And so if you buy peanut butter, you want to actually buy the one that has the oil separated at the top, because that oil is the natural peanut oil that you would stir back in instead of um, relying on palm oil, because that requires clear cutting tropical forest and then planting palm trees. This is a graph that was put out in Environmental Research Letters by Seth Wines and Kimberly Nichols in 2017, showing and comparing the effects of some other choices we can make. So if we start at the left, they're showing that yes, we can upgrade our light bulbs. However, that has a relatively modest savings every year. In fact, that's going to save less than 1 ton of CO2 emissions per year. We can hang our clothes to dry. Again, over the course of 1 year, that may not make very much difference. However, if we do it over the course of a lifetime, then we will have really reduced our carbon footprint. Washing clothes in cold water, and even better, if you replace your car with a hybrid car, like a Toyota Prius or a Nissan Leaf or others. We can eat a plant-based diet so that we are having less methane emissions during livestock production. I come from a ranching family, so I'm quite fond of grass-fed beef. There's less methane production, and there's active research into what can we feed cattle to reduce their methane production. And there's some interesting stuff going on there. We can switch to an electric car, or even try to go without a car. That actually can save quite a bit each year. We can buy green energy if that's an option. Flying. Flying takes a lot of energy. That jet fuel is highly refined, and it takes a lot of it to escape Earth's gravitational pull. Here's if we could live car free. And then again, this is not my recommendation. It is just simply something that the authors of this paper are pointing out. But we invest a lot in our children in the developed world. We drive them to soccer games, we buy them. I can't tell you how many shoes I've purchased for my sons, and clothes as they grow, etc. Now, I have 2 sons, and they are the absolute joy of my life. So I think that's a very personal decision. All right. So just to kind of reiterate some of that, taking fewer plane flights. I'm not saying don't go on vacation, but maybe think carefully about what vacations or visits you do want to make, and then stay longer. Less frequently, stay longer. Look into a low emissions vehicle, an electric car, a hybrid car, or I love the Boom Patriot here, as a way to have lower emissions. The pace of our inaction really means that when we look at predicting what future temperatures are coming our way, it looks like the higher emissions scenario is now more likely. So if we're comparing to temperatures that are where we're saying our baseline is the range of temperatures we saw from 1961 to 1979, Within another 20 to 40 years, it's looking like we are going to have the temperature rise by 6 degrees Fahrenheit. That is just going to cause overwhelming devastation in terms of heat exhaustion of people and animals. It's going to heavily impact what we can do in terms of agriculture. And for certain, we're going to have to worry about wildfire risk. We cannot let ourselves stay on this path. If we stay on this path, by the end of the century, there will still be some plants and animals that survive, that are coping with 10 degrees of temperature rise, but that is truly going to be a devastating situation. In terms of regional, state, and national options, right now, the Environmental Protection Agency, the EPA, is looking a lot into what can we do with food recovery, because there's a huge amount of CO2 produced when food goes to the landfill. So if we can reduce the amount of excess food generated, if we can donate extra food to food banks, soup kitchens, and shelters, anything that's left over we could use to feed animals if it's properly treated. And then things that are left over after that could be used to create oils and biofuels. After that, we should try and compost what remains, and landfill or incineration should be our last resort. And this sort of food recovery system is already very much underway in some countries of the world, for example, France. So there is more good news. Tax rebates are effective. On the left here, you see my electric car. I have a little Volkswagen e-Golf. It's charging for free at my local community college. And I charge it at home simply by plugging it into a regular electrical outlet in my garage. And I don't even see that cost. It's costing maybe 10 or 20 cents a night that I plug the car in. But in the spring, I really only need to plug my car in twice a week to have a 130-mile range. So I think I was able to buy this car because there was a huge tax rebate or tax incentive, um, on my federal income taxes. But those tax rebates are only available to people who can afford to buy the car in the first place. And I think that that's a problem. These tax rebates also get phased out through time. And so they tend to really favor the upper middle class and the most wealthy families, who are able to purchase these cars and get that rebate. But we ought to be thinking about how to get electric cars and hybrid cars in the hands of everybody. There's also a lot of evidence of adaptation that will make us more resilient. And so here's an example from the main street of Walla Walla near the college where I work. And this is called an infiltration basin. We know that as the atmosphere warms up, it will hold more moisture. And we anticipate and actually already see that storms have become more violent, creating more rain in a concentrated burst. It might come less frequently, causing drought conditions, and then when it comes, it will tend to switch us over into flooding conditions. And Walla Walla is a city that used to flood regularly before there were flood control measures implemented in the 20th century. So here you can see if the stormwater sewers are overwhelmed and there's water running on the streets. There's now a way for water in the gutter to go into the infiltration basin, filter in, it cleans any heavy metals from our car exhaust. We have our cars put out heavy metals and rare earth elements that are just there on the surface of the street. So any rainwater can carry those into our infiltration basin, leaving those heavy metals captured by the soil. We have beautiful plantings, and the water that then continues into the groundwater that we may eventually consume has been cleaned in this location. So remember, there's also very good news that public attitudes are changing. And again, these are numbers from the Yale survey published in August of 2018. There is public support for changing policies. People do support research, funding of research into renewable energy sources. People do believe 77% of the Americans surveyed across every county in our nation believe that we should be regulating carbon dioxide as a pollutant, and that we should set strict carbon dioxide limits on existing coal-fired power plants. If we did that, that would provide an incentive for those power plants to begin to separate their CO2 and sequester their CO2. One way to pay for that is to require all fossil fuel companies to pay a carbon tax. They have been making their livelihood by producing CO2 and helping us produce CO2 that's going into our atmosphere. We need to change our atmosphere from being treated like a garbage dump and instead treat it like the valuable resource that it is. We could regulate utilities so that they produce certain percentages of electricity from renewable sources. There's a lot of public support for that. And then provide tax rebates for energy efficient vehicles and solar panels. A lot of those rebates have expired or ended and not been continued. I would love to see those kinds of rebates continued. So, as an example, you may remember that I talked about how cement plants can produce carbon dioxide. And in Durkee, Oregon, not far from where I live, there was a cement power plant that was really important to that community, and it closed for many years. It just wasn't economical, and it was producing a lot of CO2. Well, it turns out that Warren Buffett and his Berkshire Hathaway company purchased that power plant and retrofitted that power plant to meet Energy Star certification. And that power plant, the second to achieve that certification, is now actively producing cement in the Pacific Northwest. It's there for the nearby town of Ontario, the nearby town of Baker City and Boise. So this is really a success story, and one that we should ask as a voting public to be undertaken in more locations. So most people, again, think that we need to do more to address global warming and that Congress should do more to address global warming. More than 50% of the people agreed with the statement that our governors should do more to address global warming and that local officials should do more. So we are ready for change. We've got change in some great locations like here on Main Street. And we should celebrate those, but we should continue to seek out actions that can lead to more good news. So here's a couple of thoughts to leave you with. We know what we need to do. And I love the NPR program On Being with Krista Tippett. And Kate Marvel said this quote: "We should elect leadership that tackles problems with courage, not hope, because courage leads to action and supports difficult choices." Thanks so much for listening. If you'd like some more information, these are some examples of books that talk about some of the information I've talked about today. Earthmasters speaks specifically about geoengineering, but mainly tackles the ethics of geoengineering. Elizabeth Colbert is a widely lauded author who actually won the annual prize from the American Geophysical Union for her book, The Sixth Extinction, talking about how climate change has created an ongoing extinction. It's already happening. The Rambunctious Garden talks a lot about what we can do personally and in supporting agriculture that will reduce carbon emission, or will reduce carbon from the atmosphere. And then Drawdown is very readable. I, I personally recommend this for your bathroom because these are very short segments that talk a lot about many different options. So it's a very readable book that you can pick up and put down easily. Thanks. It's been a pleasure.